Hello everybody. Today we'll be coding a bit. So we have the Skmini, which is a clone of sklearn. So I'll be continuing to code Skmini. So today's plan is to make a modulated perceptron in Skmini. I don't think this thing works. So yeah, that's a plan. So yeah. So the way I'm thinking about it is, we have uh, it's an MLP, multi-layered perceptron, that is a collection of neural network layers, which is a collection of neurons. So I'm thinking about making a neuron. It's like I've recently today watched Andre Karpathy's um, what's the name? Microgad series, Microgad episode, and it was fun. So I'm trying to implement that neural network into Skmini. Not exactly the same thing, but I don't know. I don't know if I can, but the point is to try. And this is the MLP I trained, like which I made bit earlier. I don't know this thing works. I have no idea if it works. So we're testing it. So what does this do? Uh, okay, this is for testing purposes. This is a data set turned to split. We make an object and we fit the data. So when we make an object, there is learning rate, epochs, layers, okay, weights, okay, number of layers, okay. Then when we fit the model, we take the shape of x, reshape it, randomly initiate each layer. Okay, my bad. And now we go to the forward pass. So it's probably for each weight. Oh, okay. So yeah, this was that. But I don't think this thing will work because we need a neuron object and like we need this guy. What's the plan? How can I implement backpropagation? I think we need two objects, right? So one data object and another what's it called? Huh. Okay, sorry, but sure. Another operator object. So we take two data. Oh, that's big. Opacity. We take two data, like 3 and 2, add them, and you get an answer, right? Okay. Now that this leads to the loss. Now this leads to the predicted y pred, which is used to calculate the loss. So during backpropagation, we have like we calculate the gradient of this value. Wait, this is the y prediction. Okay, if this is the y prediction, so we calculate the gradient of this thing. Do we? there will be something here. Both would be adding to create the loss function. I mean. Oh, that's cool. Then there's we have a what is called? We have a like so this will be the y predicted, and we will have an original y value. Let's say it's 6. We'll compare these two like by mean square error, but I don't think I want to, like, for the sake of the saying, I'll say we'll subtract these two guys. So we subtract these two and we'll get the loss, which is 1, right? Loss. Now we start to back propagate. During back propagation we have like the gradient of this value will be 1. The gradient of this value will be, it is addition basically, like a negative addition, right? So the gradient of this would be 1, right? So it would be this. Right? Am I right? Am I even right? Because right, we're talking about loss with respect to x. So let this be x and let this be y. So this is equal to x minus y. So when I'm taking the derivative, it's like 1 minus 0, which is 1, right? So I think I'm right. So the gradient is 1 and 1. And so the gradient is 1 here. So addition again. So nothing happens to the gradient. The gradient is 1 and 1 multiplied by this gradient for chain rule, which is 1 again. Okay, I should have multiplied two numbers, right? In retrospect, I should have multiplied, but I didn't. So what's the plan here? So this is me trying to kind of understand back propagation. Sharp, like back, prop. So what should I be doing? I need two objects. It was one in the micrograph video, the neuron object. So I want to emulate a data object. I need to make a data object and an operator object. This will contain gradient and the backward it will contain data and the children. These two will be the children of this node. So so what's the plan? So yeah, every data node will have a data node, like I'll call it neuron, right? So we have neuron will have data and children. It will also have a gradient. So will it have children? Because Yeah, I mean, I need to get from here to here, right? But that is true here. I mean, I have the loss. So, yeah, now the children. Children should be present in this node, right? Children for operator. What should this? I'll just look into what is this called? The microgrid. Mm, there's a neuron. There's a lab. No, not that. Am I talking about neuron? Because this looks like a completely different thing, man. Oh, I'm talking about value, man. It's not even neuron. Oh, value appreciates the thing you store the value. Okay, okay, okay. Hmm. So, now what? Now what? I'm audible, right? Yeah, look audible. Mm. So every neuron object contains a value object. So the data part of every neuron is a value, right? And these values contain the thing for back propagation, doesn't it? Yeah. Ooh, okay. Hmm. Okay. So what should I be doing? I have no idea. I have zero idea. Oh, what is actually present there? MLP classifier. MLP classifier variable. Mm. Number of feet. I don't know, man. I don't know. I'll probably make a clone, right? Yeah. Huh. What was that? I don't know what happened. Let's delete this. just want to copy and paste you, man. Copy. Paste. Paste. I'm not searching files, man. Control P. Apparently, I can copy paste anyways. MLP. Copy. Wait. Oh, that is fine, but I just copy all these guys here. Possibly. Alright. Now what's the plan? If that's a value object, what is the need for a neuron object? To store weights and biases, isn't it? Okay, that makes sense. That certainly does make sense. When I make a neural network, it's not a neural network that stores the value, it's the value object. Okay. Okay, that makes sense. Oh, wait. Oh, so all this is not a neural network. He said it's just a back propagation using simple operations. So yeah, this is value object. I need to make a neural network now, right? Like I don't know. I like this. Let's say. And each of these, what I say, each of these neurons contain a value object and for each neuron contains one weight value, a scalar, right? No, it contains an array of weights, each one. I don't think so, because when we have, what happens is we multiply an x with a w. Oh yeah. Oh yeah, this is a multi-dimension. It is a matrix and this is also a matrix, so we multiply each row with the each column with the row. So what I'm saying, we multiply each row with the column, so each w should be a vector. Press also best. Alright, I mean, I think I got the basic thing, so probably we should start coding. But where to start, huh? I don't know. So I think I'll just. Oh wait, this is the wrong thing, man. Okay. Mm. Oh wait, I must do the wrong thing. So MLP copy native. We will edit the MLP. So yeah. Mm. I don't know. I'll just delete all it. So I think I'll start with making a value class, just like in the microgram, and this value class should have self dot data equal to data. I should give that. And what the question is, um, should part of this thing be value class? Because I can make a separate class called the operator class, and I should write, like, come on, why not? So what should this thing have? Data and the gradient. So I've got grade equal to, let's say, 0 probably, or it should be done, I don't know. That's it. We also have a operator class, right? Class operator, and self dot data equal to data, and self dot children is a, and I'm this. Now this operator should work on two or one class, right? Right. So UBS, that's where the call function works. Honestly, I don't know how call function works. So I'll just try you return x. So I'll make a operator. Up equal to operator, operator, operator of into, into copy of 3. Yeah, that's how it works. I should probably make it bigger. Yeah. So that's it. Now what? So if that's how it works, how do you do that, man? I have no idea, man. I have no idea. Hello. Okay. Sorry about that. My electricity went off. So where are we? Um. Yeah. I probably should put a backslash here. unnecessary space here. Okay, anyways. So, no, it's printing A, B, and C. Yeah, right. That's what we're talking about. Okay. Yeah, I shouldn't be putting a backslash in that, because, okay. So there's like 2, 3, and 6. All of them have no gradient. But when I say c dot backward, that happens. One type of text is not called interesting. C is a addition thing. Oh, dot backward. Oh, this is. Oh, now I understand why I did that. Okay, okay, okay. So this is to be called, and this thing will self-dot gradient equal outdoor gradient. Okay. Now what? But why doesn't this work? Right? That's a question. What is outdoor gradient? Oh, outer grad is 1. Like c dot grad equal to 1. Then c dot backward of. Wait, do I need it out here? None of things is not callable. Oh, that was some of them. What is this, man? I'm calling it that. I don't know, man. When I call c dot backward, is it being called? Print banana. No. Okay. Oh, I'm just calling this thing, right? Why that? Not self-dot backward, outer backward. Right, this is out. Yeah. And let's assume I give it, because why wouldn't I? Backward or out. I'm just randomly trying some things, right? This is calls. I don't want that. I don't want that, and I don't want this too, right? Out is this. Fantasy dot backward. No. Okay. adding. I multiply. Okay, okay. That was how stupid because I was adding. I was okay. All right. Okay, that was just me being dumb. Ignore all of that waste of time. Sorry about that. Zero. When I say zero backward, I don't want to print this. What is this function? Probably I'm printing something. Yeah. Required add data locals data backward. Missing a self somewhere. Should I put in here? No, no. Um, what's banana on for you? Yeah, so it's just not even going there. Doesn't. If I was putting the outer data backward, it's a function. But if I do this, then it's just none. Oh. Oh. Okay. Outer backward equal outer backward. One minute. Value object has an attribute underscore backward. It means backward. Value object has now underscore. Okay, that's also right. I'm just referring to this part. You know. I'm just referring to. Pretty sure I can. Value dot add. Just say, oh, self another. Okay. Self another. If I'm not doing this, then I get none. Wait, so this thing works. Definitely works. Now I have. Now I have. Why is that not working? Like, look. Value object has an attribute. Has a. It's called attribute, right? What is method? Variables inside an object is called attribute, right? Variables inside an object is called the what? In object or in a program. Attributes are attributes, right? Okay, so value object as an attribute, none. Backward. Whenever I am adding something, right, like here, I'm setting that backward attribute as underscore backward, which is this thing. But why is there self here? Self is nothing in the right, is it? Yeah, let's go. Why exactly? Alright. I just said it out loud. Everything was fine. Alright, cool. So that works. That's cool. I don't need the banana anymore. I don't think so. Now what? So I can actually go one step backward. Now I'll just do the same for multiplication, I guess. What happened? Yeah, I'm sorry. Sorry about that. Now I have to define this thing, right? So, uh-huh. So I have to go like I have to define R, right, as out equal to this thing, and like define except no, not define underscore backward of nothing, and self dot gradient equal to out dot gradient, and the self dot and other dot no this is wrong, right, equal to wait I was just copy pasting, yeah, it is equal to something like equal to 1. I'll write it, give me a sec. Out dot backward equal to underscore backward and return out. Now we're going to write this thing out, right? So let's say we have variable c equal to a into b, right? A into b. So derivative of c with respect to a will be b, that is the other dot value. So this is my application. Self dot grad equal to other dot data, and other dot grad equal to self dot data. Yeah, that's it. Now I'm going to write c equal to a plus b. We also have abc d equal to value of 5 and e equal to c into d. And we also take like replace that by e and replace that by e, print a b c d and e. I mean for now I'll just put a backslash in here. That's oh my bad. Sorry about that. This is a b c d e. Oh, it's addition. Right. So find okay. I'll just put let this be for different numbers. So 2 plus 5 6. 2 plus 4 6 plus multiplied by 5 is 30, and again it looks correct. Well, that's just one problem. It's not back propagating, right? It's because I didn't write the search the traversal. I mean, that makes sense. Now I should write the traversal, but where? Let's look at undergrad for the micrograd, because like I have the recruitment. Oh, he defined a function called a backward. Where? As a value, okay. I don't have that. But why is that even required? There is a, oh, he defines this as underscore backward, which is, because we define this as underscore backward. This can be bad. I'll define it as back propagation, right? Right. Okay, so when you take a value and run this backward, oh, okay, that makes sense. That makes sense. I'll define it as back so let's define back propagation given as self, and what this thing it does is this, like trav trav traverse traverses through the tree till it reaches the leaf nuts and applies gradient to each of the nuts. So this is what this thing does. That's cool. Now what? So I'm supposed to do that, right? So how will I be doing that? Yeah, not E. I'll just draw that, right? So right. So okay. Okay. So I'll have like uh not copy paste copy paste. Right. We have two knots. Add to get one. We have another knot. Multiply to get one, I think. And that's it. Oh, ignore this S. So what is this? That's better. Where is the text size? Small. Okay. Okay. So we have 2 and 4. We have 2 and 4. We add them to get 6. We also have a 5. We multiply them to get 30. Okay, numbering of E. Okay. Now I make a round of the final value. So T, then 30. Come on, man. Now I have to make this thing. Rice. Pretty sure that will encompass 30, right? Now I need some arrows. That's kind of cool. Right, that's cool. So this is our back propagation, and what is this? So this is our current function, right? This is our function. Okay, now what? So when I call this and say backward, the gradient of what these things should be filled, and then the gradient of these two should be filled with respect to 6, right? So how can I go from 30 to 5? 30 is an addition node, it's a multiplication node, this is an addition node. And multiplication node has children which will give the object for both these two, which points to both these two, right? So I can, yeah, I should be using children to jump through this thing. Okay, that makes sense. That's simple. So how to do that? For child in self dot children, right? I can check if it's a leaf node by looking if the operator is empty. So like I go here, I mean first I'll just self dot backward, right? Self dot backward, I run this, then the gradient of these two guys will be filled. I should be using that gradient of what these two will be filled, right? Then I can go to 5, say, and if it is a like operation node, OP node, then I want the back prop, right? So but this have to happen. Now if it's an open node, I'll just recursively call back prop. That would work, right? So if child dot op, say if not child dot op, if child is not out, right? That is, if it is not an operator node, I mean no. If the child is an operator, OP node, then child dot back prop. Can I do that? I think I can. So E dot doesn't work. Interesting. I'll try to print it out. Okay, that works. So self backward works because gradient of these two guys are getting filled. Then it goes to each child. I can just print the child, print child. Oh, no child. Print the child or children. No children. Why don't you have any children? You have children, man. What do you mean? It's underscore children? That's just stupid, isn't it? My bad. Oh, it works. Well, we will see if it's that correct. So we'll manually go through backpropagation here. Like the gradient is 1, the gradient is 1 into 1, which is 1, the gradient is, no, these are getting multiplied, right? So the gradient will be the opposite thing, 6 and 5. Here thing is just getting added, so the gradient will equally be split between, will just be the same for both 5 and 5. So 5, 5, 5, 6 and 1. Yeah, that looks right. Yeah, that is right. Whoa, that was easy, man. I was expecting that thing it to be harder. Okay, I mean that was fast though. I wasn't expecting it to get. Okay, anyway. So as we have a backpropagating expression thing. Honestly, probably I should write all these in a different module and import it, right? Yeah, I'll think about it later. So, to make a neural network, I would need addition multiplication, maybe an activation function, right? So, maybe ReLU. Let's start with ReLU. So let's define ReLU and self and the self. ReLU is a what's it called? Binary unary operator. Yeah. So out equal to self dot data if self dot data is greater than 0. Else, what happened there? Okay, else. Oh wait. Whoa. Yeah. I mean, I can just write max, right? What am I doing? Maximum of self dot data into 0. Okay, I was just thinking. Now I have to. Oh, how do I back? Okay, I'll look it up. ReLU Wikipedia rectifier. Rectifier. Okay, just why is it rectifier? Right, ReLU, man. A ReLU, rectify linear unit, right? How you can okay. Express mod x by 2. Yeah. Leaky ReLU. Leaky ReLU is a small positive gradient. The unit is not actually helping to mitigate the vanishing gradient problem. Parametric ReLU, I know that. X of x is greater than 0, a into x otherwise. Okay, probably a will be a small number, I think. Maybe that's the thing. I mean, then it's just this, right? A, so it's probably not a small number. Note that for a less than or equal to 1, this is equivalent to a. Non-linear variance. Gaussian, okay, I don't know. What I need is not here apparently. Doesn't matter. So values gradient. how this is ReLU, right? So the gradient of ReLU at any value equal to less than 0 is 0, right? This is positive gradient, this is negative gradient. Yeah. So if the number is greater than 1, gradient is 1, otherwise the gradient is 0, isn't it? Yeah, now I'll ask, what is the gradient of ReLU? Yeah, that's right. Okay, that's cool. So I don't want to write that. Define backward. I'll do that. Define underscore backward. So if out equal to 0, self dot grad equal to 0, else self dot grad equal to 1, and that's that, right? Yeah, I think that's right. So out dot backward equals underscore backward, and the return out. That looks correct. I'll now have an f naught equal to, how do I type work? How does that work? Value dot, okay. So e dot ReLU, and replace e by f, and replace f fe. Oh, integer object has no attribute backward. Integer object. Who is an integer object? And oh yeah. Oh, so the max function just works. Oh, okay, my bad. But why didn't backprop work? Probably I'm like children did I? Yeah, backprop. It's a operator, right? Yeah, it's an operator. So I should put like underscore operator equal to the value, and like underscore children is actually just self, right? Yeah, that works. So that means we have green, we have this thing, we'll have this thing, we have this thing. The value will just be text and 30. Value of 30 is 30, so gradient here would be just be 1, right? So yeah, triple 5 and 6, triple 5 and 6, 1 1 5. Oh, right, cool. Also, now what? Backprop. Yeah. Now what? Now, I have to build the neural network. Sure, no, right? I mean, ideally, I should be writing more these things, but I think I should be writing neural network right now. So we have a class neuron. I probably initiate this to none at the beginning. Right. I have a class layer, and initiating testing is important because this will have a number of neurons. Right. So self dot number of neurons equal to number of neurons. Okay, I'll just give that. We also have a class. Multi-layer perceptron and different underscore init self and number of layers. Or you know what I can do instead? I can just give a list containing the layer config. That would be better. So I'll just name it layers and I will extract that thing from that layers and run it. I bet. So I'll just self dot number of layers equal to length of layers okay. So ideally what should happen when I initiate a MLP layer, I probably rename this to MLP graph later, but bear with me. When I define MLP, I should have all these things initialized, right? Like I would say a model equal to MLP of like 2 in the like 5 neurons in the first layer, 3 in the second, 1 in the third, and it should work. Huh? Okay. It should work. And then I should be able to MLP data fit. I mean model data fit. So what should happen during fitting? Well, and I have no idea. Okay, hard part comes back. So I think what now what? idea, so I'll just do it. Self dot layers equal to layers. Not really. I should have a list of layer objects, right? And each layer object should be a neuron object. Yeah. So it's empty for layers, for layer in layers. Self dot layers dot append a layer object with the layer value. That looks right. The same thing happens here for neuron in I should name it data or object or MLP or something, right? I'll just name it data for consistency, because this is the main data present here. Probably change it later. Data equal to neuron of I for I in wait. There will be 3, so I just need 3 neurons, right? Yeah, I run here. Neuron for I in range 3, yeah. I'll just print layer 2. Define underscore representation underscore self return f string of layer object with the self data and here we will have define underscore upper self return neuron object with self dot w and self not really self dot b printing. So we have a what I want is 531. So we have first layer. Is there some way to make a count? This is enumerate, right? What am I doing? Why is being printed anyway? Okay, printed data. I want to run this. Define underscore representation underscore self return a string of MLP with self-data data. So we have MLP with the layer, with the neuron, but I have no way to count it, right? It's just kind of sad, otherwise I could have like layer 1, layer 2, but it works. So neuron 3, no. Second layer with the neuron 3. Okay. Every layer has 3 neurons, which is wrong if I am right. So why is there 3 here? One, two, the pot pipe. Second layer for 1, 2, 3. Third layer 1, 1. That one, 5, 3, 1. That's exactly correct. Now what? Now I have to define the shape of each. Do I? Because our weight. So now let's think about neural networks. Right? All this is about expressions. Now, boys and girls, we go to neural networks. We'll go here. Right. So first we need a circle. I think this will do. So we'll have like 5 of these guys. Three here. One more here. So this is a neural network, right? We actually have a connection like here. Everything is connected to every other thing. And here also. Now what? This is a layer. This is a neuron. This is a neuron. This is a layer. This is an MLP. Right? So when I say it's how about right? Right. But when I define an MLP, I think I cannot. So the thing is, you know, what is the shape of the input? Like x dot shape equal to there will be 100 instance and let there be 8 features, right? That's the shape. So this means that I would have like a this will be multiplied by the weight matrix, which will not be present on the neurons but actually on the edges. So what should be the weight of the edges? The kind of like 8 by something. I mean, the weight matrix should be 8 by some random thing, anyway, right? So it should. So it's not 8 by n1, it's 8 by length of layer 1, right? So each of these things should have a each of these neurons will have a matrix. But how can I do that? Because there should be a value object for me to back map on it, right? I don't know, man. I have no clue. Okay, I can understand. But I have no clue. I have zero idea. I don't know. Hmm. But what I do know is that the weight, when we initialize the weight, we need to know the shape of the input, right? Because random weights, yeah. So yeah. So I think this is right. So when I define fit function with an x and a y value, that's when the game changes. That's when everything starts. What should happen? Well, I need the shape of x. X would be identity numpy. So Python import numpy as numpy. Import numpy as numpy. X equal to numpy dot random dot random number of 10, 20. x dot shape. So 10 is m and 10 is the 20 is the number of features, right? So m comma n equal to x dot shape, and now what should I do? I should be forward pass, then there should be a loss calculation, then there should be a backward pass. And you update the parameters. But before that, I need the parameters, right? So every time I'm using fit function, it will randomize all the neurons, but I don't want that to happen because I want to iterate all the previous things, right? So if not early here defined randomly initialize the weights. Okay. So now I need to, I need all the parameters, right? Yeah. So neuron, I need like a self_underscore parameter equal to set of self dot weight and self dot biases. Now, what should the underscore? Self dot parameters is an empty list. For I in self dot data, parameter for neuron dot parameters for neuron in self dot data. How would that would work, right? Neuron data parameter for the what if I just print self dot parameters. That is right. Oh, for MLP, self dot parameters layer data parameters for layer in self dot data print self dot parameters. Man, if these things were NumPy arrays, it would have been fun, but they are not. That sucks. Wait. Can I just do this? for parameter in self dot parameters, print parameter. What I get? This is the first layer, second layer, and third layer. Right. And I think I'm gonna stop here. So I don't know, man. I'll think about it later. Mm. Yeah, I think that would be it for this episode. Thank you for watching. Yeah, see you soon.